Okay, I have started the recording. It's 4 p.m. Yes. So today no one has joined. Let's wait for few minutes. Day by day, I'm observing that people are not joining the session. Okay, somebody has arrived. Okay, welcome, Patralekha. So today you are the first one. Let's wait for other people to join. Then I'll start. Someone have joined and left. I think I. Who else is there? Shivam is there. So both of you are like a regular student. Others are just not joining. I don't know why. Probably I'm not teaching well. Motivated student. Okay. Good, good. So I think probably other people will not going to join. Anyway, if they join, they will join. I'll admit them. So I'm going to start now. Let me check my video is recording or not. Yes, it is recording because that is most important. Otherwise, I don't have any proof to show them NPTEL team to that I have uh, taught you guys. So yeah, welcome you all. Today is our live session 6, and as you know that I am doing PhD from IIT Kanpur under the guidance of Professor Pratik Sen, who is the instructor of this course. So without wasting any time, let's move on to the next question, to the today's first question. So this question is from the previous year's assignment number 4. So are you able to see my screen? Am I audible? Visible? Yeah, okay, fine. Okay, then tell me this first question is sample has a lifetime less than 20 picosecond. Uh, okay, somebody wants to join. Devendra, yeah, that fellow, I know him. He has joined. Okay, welcome Devendra. Hello Devendra. So for now, I'm meeting you. Anyway, welcome Devendra, and I have just started this session. So today's first question is the seventh question of the previous year's of assignment number 4. So try to solve it. I hope you have finished watching your these week's lecture. If you want to speak, you can turn on your mic and unmute yourself and speak. Because I know you because you have joined one of my class, Devendra. So I know you. And these two, Patlekha and Shivam, they are like the regular customer of my this class. So I know them very well. Anyway, moving forward, try to solve this question. A sample has a lifetime less than 20 picosecond. Among the following instrument, the best technique to determine the lifetime is: one is nanosecond TCSPC, picosecond TCSPC, fluorimeter, fluorescence subconversion. Obviously, answer is written, explanation is also written, but I will make, or you need to make sure that you have understood. Of course, I will going to explain, but okay, some who is writing? Okay, Patlekha is saying upconversion. Yes, it is fluorescence upconversion because TCSPC, this the range of the TCSPC, or I would say the resolution is around, yes, as in TCSP 20 yes. So it is like 25 picosecond to let's say 500 picosecond. So this is the resolution of TCSPC. This is picosecond TCSPC. Picosecond. So I am talking about this second option. Nanosecond, it is much slower than the picosecond. So obviously the time scale will be higher. But here the question is asking for the instrument who can, that instrument can measure the lifetime of 20 picosecond or less than the 20 picosecond. So resolution of the instrument should be much higher than this, or much be higher than the 20 picosecond. Then you can measure. It is like you have like meter scale and you want to measure centimeter. So that is not possible, right? But you have millimeter scale, then you can measure the centimeter. So just like this. Okay, but option C, here option C is fluorimeter. Fluorimeter is like, this is this measures only steady state phenomena. Nothing about your this, what do you call, the time resolved. Okay, and the last one is the fluorescence upconversion. So upconversion, if you have studied lecture number 21 of this course, you must have seen that in the video that sir has told already, that in the upconversion They measure the time, I mean the lifetime decay using NLO material, non-linear optical material, which generates the like passing in that if the light is passing of 800 nanometer and 600 nanometer, it will sum these frequency or the wavelength and generate that value. So by summing this, you will get the low value than this, which means around let's say 700, which means for 600 and 600 and 800 it is not true that I'm going to tell you the calculation also. Okay, let okay, he left already. Anyway, no problem. So calculation is like 1y 800 plus 1y 600 equal to 1y lambda. Then you can calculate the what is the yeah your this some frequency generation this lambda. So obviously it is not 700. 342. Okay, maybe 342. Anyway, so then by using this NLO in the up conversion, you can generate the higher frequency, higher lower wavelength, lower wavelength, and higher frequency with higher resolution. So in the fluorescence up conversion, you can measure the lifetime in the femtosecond region. So provide femtosecond time resolution, making it a best technique for lifetime less than 20 picosecond. Okay. Okay to you guys. Shivam is fine. Devendra, Patlekha is saying yes. What about Devendra? So should I move forward, Devendra? If it is okay to you, then there is no problem. Okay, I'm not getting any response from you. Let's move on. So next question is among the following property one, two, three, four. The property a laser does not have is this you need to answer. This is written. It is here. Like out of this four property, which one is not the property of laser? High monochromaticity, low divergence, high power, low spatial coherence. Low spatial coherence. Yes, you are right. Because laser produce the high spatial and temporal coherence. It is like the only the one point of one wavelength. Ideal situation. Let's say this is your laser. So it produces as a single wavelength light or pulse, single wavelength pulse or light. Uh, okay, so single wavelength means high monochromaticity. So this is the property of the laser, but the question is asking for which is not the property of the laser. So high monochromaticity is the property of the laser. Next is a low divergence. Low divergence means it will going to diverge, which means it will not focus only this point. It can also like somehow it will reflect, diverge, or it will go this side also at this side. So at let's say this is your wall. So if you point a laser to the wall, you will get something like this round, this much of area of the light from the laser, and at this point, midpoint, it will be higher. The intensity will be higher, brighter, or and the here at the corners intensity will be lower if it is diverging. But this laser is designed in such a way that it should focus only on one point. So it will only going to focus on one point, which is I don't know how to take. Okay, fine. And the color. So this point only. Fine. So this is also the property of the laser. Next is high power. Obviously, if only one light, one wavelength pulse is coming at only one point, which the space is very less. Obviously, the power will be high. So this is also the property of the laser. So low spatial coherence means whatever I have already explained this. So this will be your answer, D. So this is not the property, low coherence, low spatial coherence. Good enough? Three of you? Shivam is okay. Patlekha is also okay. Devendra, you are not replying. Are you not able to listen to me? Are you not interested? Or just don't want to answer? Because since you are attending the class, if you are, yeah, last time you have said you are in the library, so no problem. You don't have to speak, but you can type it down, or just thumbs up, or because you are also in the class, you are giving your time. So that is why I need to make sure that you are also learning. That's the whole point. Okay, seems like you are not interested. Moving forward. Next question is, why is it important to keep the photon detection rate low in the TCS-PC instrument? This is, if you watch lecture number 20, you will get the answer. Anyway, I will going to explain. So it's now your turn. You need to take your 1 or 2 minutes, think about it, read it down the explanation and answer, and then explain. Then there is no problem. Yeah, Devendra, you want to say something? Because you have unmuted yourself. So Okay, no problem. Try to solve this question. Any guesses? Okay, Patlika is typing something. Photo. So that the first emitted photon is not the first detected photon. Means? Yeah, yeah. Okay, okay, yeah. Why it is not? Why it is important to keep the photon detected rate low in the TCSVC experiment? Because the first emitted photon is not the first detected photon. If that is the case, if your first emitted photon will be first detected photon, then always you will get the first emitted photon. Then no, oh, then then this is time intensity. All the detected photon will be at the shorter range here. So your spectra will look something like this if the rate is higher. If rate is low, you'll get the actual spectra, actual lifetime. So that is why we have to keep the photon detection rate low. So option A is to prevent the signal from the distortion, and that the rate is 1 or 2% of the 1 or 2% of the your repetition rate. So in the explanation, it is written in the TCSPC the system operates under the single photon per cycle condition if multiple photons arrive in the same timing cycle. The distance. Yes, Devendra. Yeah, you have raised your hand. Tell me. So, if multiple photons arrive in the same time cycle, the detector records only the first one, causing the pile up distortion and leading to the incorrect lifetime measurement. Keeping the detection rate low, 1% of the laser repetition rate, ensures accurate data collection without vising the decay profile. Fine. Okay, this. Okay, Shivam is fine. Fine, sir. Devendra, as usual, probably will not reply. Moving on to the next question. Which of the following solvent is expected to exhibit the fastest solvation response time? So, benzene, acetonitrile, water, ethanol. Tell me the reasoning. Reasoning is also written, but you need to understand and tell. Water, okay. Tell me why water? Fine, sir. Okay, Devendra. Finally, you are replying. Due to its small size, it will reorient fast. Yes. So explanation is also written. The solvent's response time depend on the dielectric relaxation time, which determines how fast solvent molecule can reorient in the response to change in solute electronic states. Which means, let's say your solute is here S0, S1. From here to here, it is going. The molecule is going to the excited state, and around this molecule. So I'm drawing this molecule like this. Let's say this and this. Okay. So now after excitation, your position, your system is like this. Okay, higher dipole moment. So I'm taking the condition mu e is greater than mu z, which means mu e is the dipole moment. Okay, so dipole moment of E means excited state, G means ground state, excited state. Okay, so if this fluorophore molecule will excite will be excited from here to here, its dipole moment is changed, and I'm saying this mu e is greater than mu e. So in that condition, if that, let's say here water molecule is here, water molecule here. So in similar fashion, it will be here. Other water molecule will also be there. Anyway, I'm just roughly drawing. Okay. Anyway, so due to this change in its dipole moment, these water molecule, these water molecule will reorient in will reorient themselves to neutralize the effect of this solute, the solute of the dipole moment, which has been created or being increased or decreased, being changed by your excitation. So it will take some time. This water molecule will take some time to reorient themselves to neutralize that effect, and that effect is called the this solvents response time. So so the energy will be stabilized, which means of the excited state, which means that these state these state will go to here, something like this, after certain time, because these water molecules have rearranged themselves, so their energy has been decreased. Then from here you will get the fluorescence. So they are asking about this process. this process, from this position to this position. From here to here, whatever time is taken by this solvent molecule. So which solvent out of these four will take less time? Question is this. So obviously, which will have small size, first thing, and will have the capacity to neutralize that effect, which means if they have the, let's say, strong hydrogen bonding. So polar solvent with strong hydrogen bonding, small molecule size exhibit the fastest solvation time. So in the water, let's say if this is water, this fluorophore is solvated in the water, then it will take less time compared to, let's say, benzene. In water, it is taking 10 picosecond. In benzene, let's say it will take 30 picosecond from this position to this position. Okay, good to go, both of you, three of you. Okay, Shivam is fine. Patlika is also fine. Devendra? Yes, sir. Okay. So I'm moving forward. Okay. So this is the question. This is the assignment of this year. Assignment week 5. So a question one is, which observation confirm dynamic quenching? Lifetime unchanged, but intensity decreases. Both fluorescence lifetime and intensity decreases. Absorption spectrum changes. Fluorescence wavelength shifts. Quenching itself says, let quenching means something is decreasing. Tell me. Oh, somebody has written something. Fluorescence lifetime and intensity both decreases. Yes, of course. Because in dynamic quenching, what happens? That addition, if you add, let's say there is a fluorophore in your system, and you are adding a quencher. So what it will do? It will quench the emission intensity as well as the fluorescence lifetime, because this quencher will going to decrease the lifetime or intensity via non-radiative transition. So by adding the quencher, it will, let's say, form some complex, or it will take out the energy as a heat. So in that way, it will going, or it will become, let's say, let's say, let's say fluorophore and your quencher, they will form the complex. Then this complex is non-fluorescent. If fluorescent molecule is alone, it is fluorescent. But if this quencher is coming, it will make this non-fluorescent complex. Non-fluorescent complex. So by the non-radiative decay, the lifetime and the intensity will going to decrease. So dynamic quenching introduces an additional non-radiative decay pathway which results in both a decrease in fluorescence lifetime and intensity. So option B is correct. Anything you want to want to ask, or is it okay? Shall we move forward? Okay, Patrika is saying something. It should be static if ground state complex formation occurs. Okay, that is fine. That is fine. Whatever you are saying, it should be dynamic or static. But let's say if ground state complex is forming, that means it is your then it will be uh, static quenching. In dynamic quenching, the excited state fluorophore intensity or lifetime decreases in the presence of the quencher via diffusion or collision. Yes, it is right. Yes, yes, yes. You are correct. I'm just giving you. Let's say. Okay. So let me change little bit. This is H nu F star. Now it is fine. I hope. Yes, yes. Now it is fine. Yeah. Oh, so yes, you are right. So in the ground state, in the excited state, this will going to happen. Then, because of this non-radiative decay pathway, both the lifetime and the intensity of the fluorescence will decrease. Well, this question is not asking about the dynamic and static, but still we have discussed, as Patlika has already briefly explained how this dynamic quenching has like occurs. So dynamic quenching means that fluorophore and your quencher will come close to each other, collide, and because of that, the quenching is happening. Maybe it will form this excited state complex, or it will creating some non-radiative decay by any means. And in static means in the ground state, if you are adding the quencher without excitation, let's say your molecule is in the solution, like in the solute, so you have the solution and you're adding the quencher. Then let's say before adding the quencher, you have measured the emission intensity, and that turns out to be, let's say, 5000 AU. This is the intensity. But after adding the quencher, if you measure this, what you call emission intensity, it turns out to be, let's say, 3000. Then you're, obviously I should not explain like this, because then you cannot differentiate that it is dynamic or static. So to differentiate, we have other, there is other method or to determine how it is dynamic or static. But and both the quenching have the same expressions also. So static means in the ground state your fluorophore is getting quenched by your quencher. That's it. That's it for now. In maybe in the coming question we have some questions, then it will be more clear and I will explain. Okay, fine. I'm moving forward. Patlika already explained. I know it. No. So yeah, yeah. Okay, Devendra is also fine. Okay, moving on to the next question. A fluorophore shows intensity of 500 AU at lambda max 450 nanometer in the presence of the quencher 0.2 molar. The intensity decreases to, this is one part. After adding this, let's say 1, this is 2, 250 AU. The Stern-Borman constant is, okay, you know already, Stern-Borman quenching, or this equation, Stern-Borman equation is K Stern-Borman. I think all the parameters is given. If fluorescence intensity of this, oh, this should be I0 then this should be I0, because if fluorophore shows fluorescence intensity 500 AU at this, in the presence of the quencher, after adding the quencher, intensity decreases to 250 AU. So which means this should be your I. This should be I. According to this equation I am writing, this should be I. And what is given? This is given now. This is given. Quencher concentration is given. The intensity, the Stern-Borman constant. Okay, they are asking about this. Stern-Borman constant. This is simple. This you need to just figure it out by 500 divided by 250. It will be equal to 2, which will equal to plus 1. KSV quencher is 0.02 molar. Calculate 2 minus 1 is 1. 2 minus 1 is 1, equal to KSV. V, this should be V into 0.02, which will turns out to be KSV equal to 1 divided by 0.02. So multiplied by 100, it will be turned up 100 by 2, so 50. And its unit, what will be the unit of this? Okay, in all the answer it is written already, because this is molar, inverse of the quencher concentration unit. So this concentration means molar, molar inverse. Answer is 50 B. All good? All three of you? Yes, Patlika is fine, Shivam is fine. I hope Devendra will reply. Any question, Devendra? Sir, but answer C. Huh? What is answer C? Oh, correct answer is C. No, this is mistaken. 100%. This should be A. No, this should be B. This is wrong. No, we are doing the calculation. No. C is wrong. 100. This question is from this year only. Yes, this year only. This is the second question. So probably they have the who is the TA. I am one of the TA, but I am not making the question. Probably who is making this question have made mistake. Okay, Devendra. Answer should be B. Okay. Next question. A fluorophore here your Stern-Bornmal quencher constant is given 150 mole inverse. If the initial fluorescence intensity I0 is 600, what will be the intensity B at quencher constant of? Oh, same question. Just same question. I0 by I 1 plus KSV quencher constant. You have all the things. I0 is 600 divided by I you have to calculate. So 1 plus what is KSP? Unit is fine. Molarity inverse. This is 0.2. You need to figure out 1 plus 150. Let's say 300. 2. So this is 3. Total 4. So it will be like 600 I equal to 4. So I equal to 600 divided by 4 equal to I. Turns out to be 150. This time answer is also given wrong. I don't know. Answer should be A. This is wrong. Should be A. Explanation is also saying A. Probably T is not giving enough time. Probably who is giving making this question. Devendra is saying something. Question 2. Okay. Question 2. This question. Question 2. सर असाइनमेंट में आंसर 50 एक्सेप्ट नहीं हुआ. बी. सर रॉन्ग हो गया. Okay, probably because explanation, the solution they have given after your submission. But if your TA have given the answer C correct for this question, so if you mark B, your answer automatically will be wrong. But actually, B is the correct answer. So in the portal, they have uploaded the wrong answer. So that is why probably this problem is coming. But believe me and trust me, this answer is B. I cannot do anything for your this question because I'm not taking care of making the question and uploading it. Probably who is uploading they have also made the mistake, because in this question also, question number 3, answer is also wrong. Again the answer is wrong. So I have no clue why the answer is wrong. So in this question, Devendra, you must have this. Again, you have got the incorrect answer, like the wrong answer. If you have given A answer, they have not accepted your answer probably. What about this question? Question number 3. Let me check. My video is up. Yeah, video is recording. 51 minutes. So what answer you have chosen for this question? Question number 3. Devendra, Patralekha, Shivam. Nobody is replying. I have no clue. Should I move forward now? A, yes, A is correct answer, but I'm. So you have given A, Patlekha. Like you have chosen A answer. Yes. So they have accepted your A answer or not? No. Okay. So probably the T of this course is who is giving making this answer, or maybe sir. So I don't believe sir is making question, because he will not going to make such kind of mistakes. So the TA of this course is not giving enough time to make this question. So he or she should have like cautiously checked their question and answer. Anyway, I will, because I know the TA, so I will inform that person personally. Patlika, yes, no, yes. Okay, Devendra is written. Stern volume again. Stern volume again. What he has written, I have no clue. I0 something t equal to 1 is to equal to this 1 plus 150 0.2 1 plus 3 equal to 4, so I is to 6 150. Yes, that calculation I have already done. The same calculation I have already done. Okay, so can I move forward now, or you have any query? Seems like Devendra have something to say. I feel so. Patlika is okay. Shivam is also okay. Okay, no problem. I'm moving forward. If you have any query, just stop me in between. So the next question is slope of Stern-Normal plot from intensity data is 150 per molar T. So 50 molar T inverse. While lifetime data gives slope of, okay, okay, this slope from the your I0 by I, and this slope is from your tau 0 by tau, which is equal to 80. So ideally the equation I am writing again and again, right? And same equation for both the cases. Which statement is correct out of these two? This you must have studied. Explain it to me. So according to this equation, your slope KSB from both the measurement, intensity measurement and the lifetime measurement should be equal. But the slopes are different, which means that it is not only the dynamic quenching, because if lifetime is changing, it means that it is dynamic quenching. How so? Because because this dynamic quenching is your excited state phenomena. You are exciting the molecule, and that excited molecule is or will going to quench by the quencher at the excited state only. Hence, via non-radiative transitions. So basically, the non-radiative transition will increase. Hence, your lifetime will your decrease. Lifetime will be decreased. So this is your dynamic quenching. And 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 for intensity also, here in fluorimeter, if you measure fluorescence intensity, the intensity will also going to decrease by adding the this quencher. But measuring only the fluorescence intensity, you will not going to determine that it is your static quenching or dynamic quenching, because in both the cases, let's say at the ground state, if you are adding a fluorophore, it is at the ground state. If it is going to um, if it is going to this making the complex at the ground state, then again, after, let's say, if you measure the intensity of of your solution without adding the quencher, some intensity is coming, let's say 500. Again, then you have added the quencher, intensity is coming 300. So intensity have decreased from 500 to 300. Fine. But you cannot by if it is forming the ground state complex, then also the intensity will decrease. Even if it is dynamic quenching, you are exciting the molecule, your quencher is already present there. Again, it will form the complex at the excited state. Intensity will decrease. you will not going to understand that or differentiate that what type of quenching is happening. Okay, so that is why you have to take the lifetime of your sample before adding the quencher and after adding the quencher. So what you will observe, by adding the quencher, your lifetime will decrease if it is dynamic quenching, because at the excited state your fluorophore is getting quenched by the quencher, right? So that you have excited the molecule, it is in the excited state, but it will not going to radiate by the heat dissipation. It will come down to its ground state. Hence non-radiative channels are or decay has increased, which means your lifetime will decrease. If lifetime is not decreasing, what does it mean? That in the ground state you have added the quencher, it has formed the complex, but now you have it already formed the complex at the ground state. Now you can excite the molecule. Okay, that complex molecule will also going to will go to the excited state, and your this, let's say, not 100% all the molecule will going to be from the complex at the ground state. Some are F, and also there will be F and Q. These will also going to be excited, will go to the excited state. This F fluorophore will also going to go to the excited state, but at the ground state this complex become non-fluorescent, so it will not going to affect the lifetime, because anyway it will not going to radiate. But this fluorophore is getting excited, and without any problem, without any reaction at the excited state, it will come down to the ground state without any change in the lifetime. So by adding the quencher, your lifetime is not changing at the lifetime is not changing by increasing the concentration of the quencher, which that said that which indicate that it is ground state quenching. The ground state, not ground state, what is that? Static quenching. Ground state complex formation is happening. So it is static quenching. So now you have to tell me the answer. The answer is C, mixed quenching present. If dynamic is there, if dynamic was there, only dynamic was there, then these slopes has to be same in both the cases. But lifetime slope is different than the intensity slope, which means there is a mixed quenching is there. Okay, Patlekha, Shivam, Devendra, all three of you. Shivam, Patlekha is good to go. What about Devendra? Devendra is also okay. Okay, moving on to the next question. A Stern-Bolmer constant. A Stern-Bolmer constant again. So lot of questions from the same equation probably. Okay, 800 is observed for the fluorophore with a lifetime of 20 nanosecond. Lifetime 20. Is the quenching diffusion controlled? So quenching diffusion constant. So you need to then find out the quenching constant. So in this Stern-Bolmer, this I0 I C correct answer for which one? This question, right? Yes. This correct answer. I equal to 1 plus KSB and this KSV is equal to KD and your tau 0. This is and here what is Tristan constant of this is object for fluorophore with like, okay, so this is tau 0. So just 5,000 800 mole inverse equal to KD. You need to find it out. Tau is given 20 nanoseconds. So if you just calculate it out, what is the KD? KD turns out to be 800 divided by 20 into 10 to the power minus 9. Then it will become second, and this is mole inverse. So mole inverse, second inverse. Okay. So it turns out to be plus 9, 20, 40 into 10 to the power 9, which means 4 into 10 to the power 10. And the unit will be mole inverse, molarity inverse, and this second inverse. Okay. So to answer is KQ equals KQ, KD I have written. Okay, this should be KQ, quenching. So option A and option C. What is the quenching diffusion control? This can, so basically they are asking it is dynamic quenching or it is controlled by the diffusion, which means it is dynamic quenching or not. So the limit of diffusion limit is 10 to the power 10, and the KQ is coming more than that. Whatever you are getting, the 4 times 10 to the power 10 value exceeds the diffusion limit, indicates that the static contribution is there in this quenching. Hence, quenching is not purely diffusion controlled. Okay, Devendra have given already the answer. What about Patlika and Shivam? And then we will move to the next question. Okay, both of you given fine. Everybody is fine. Everybody is fine. Fine. Okay. Efficiency of fluorescence resonance energy transfer. Fluorescence resonance energy transfer, FRET. It depends on efficiency of fluorescence resonance transfer depends on. So if you remember the efficiency formula, I don't know, in the lecture I have not. So there's a long formula. This formula is long. So anyway, this is proportional to 1 by R. So R is the distance between donor and, this is your donor and acceptor. So this is, let's say this is the distance between them. So it is the inverse, the efficiency is inversely proportional to R to the power 6. So hence it is extremely sensitive to the distance between donor and acceptor molecule, and that R I think the maximum limit for this FRET is 10 angstrom or something like this. I don't remember exactly, but something like this. Anyway, so basically, what you mean? Let's say this is what I mean. Let's say this is your donor molecule. This is your donor molecule, and this is your acceptor molecule. This is your acceptor molecule. So their distance, this has to be close. Let's say this distance has to be 10 angstrom. Then the energy transfer will be there. So donor acceptor distance is important for this transfer of energy. So answer B is correct. Maybe I don't remember. This is 10 angstrom, 10 nanometer, some 10, 10 2 to 10, some. values there. No problem. Nano 35 nanometer. Probably nanometer. Probably nanometer because yeah, probably nanometer. This should be nanometer, I guess. It should be nanometer. 2 to so the typical range is 2 to 10 nanometer. Probably. You just Google it. You'll get the. I don't remember the yeah 2 to 10 nanometer. Patlika is saying so. Yeah, 2 to 10 nanometer. Anyway, yeah. Thank you for help. So yeah, you have understood this question. Patlika is fine. Shivam is fine. Devendra is fine. Okay. Moving on to the next question. Increasing solvent viscosity leads to this we have to read it out all the options. Increased dynamic quenching, decreased dynamic quenching, increased static quenching only, no effect of the on the quenching. So basically this question is also from this quenching. So by increasing the solvent viscosity, what you are expecting? Explanation is also there. So explanation is written dynamic diffusion depends on the molecular diffusion. So how efficiently they are colliding. So high viscosity means that the slower diffusion, which means both the quencher and the chlorophyll will the rate of collision will be reduced. Hence, it will reduce the quenching efficiency. So if it is dynamic quenching, okay, Patlika is writing dynamic quenching decreases as it is depend on diffusion. Yes, dynamic quenching is depend on the this viscosity of the solvent. B correct answer. Yes, B correct answer. Okay, so I think he has understood what about Patlika. Oh, Patlika also written. What about Shivam? Okay, moving on. Next question. Increasing temperature typically enhances. Out of four answer, like out of four options, which one is correct? B. Yes, because increasing the temperature increasing means your system is getting heat from the outside. So all the molecule will vibrate or treble more efficient or fastly compared to initial condition. Hence, your dynamic quenching will be effective. So here written is increasing temperature typically enhances dynamic quenching. Yes. So dynamic quenching depends on diffusion, higher temperature, faster molecular motion, and increased collision frequency. Hence, quenching increases. So option B is correct. Fine, all of you, because there is nothing to nothing to explain because already like same topic again and again, same question. Yeah, all of you are fine. Nothing is there to explain anyway. Okay, next question. Fluorescence of convergence spectroscopy measures ultra-fast fluorescence decay by. This is what I was telling you. The mixing. So answer of this question is mixing fluorescence with delayed gate pulse in a non-linear crystal. So upconvergence uses non-linear optical mixing to convert emission into the higher. That is what I was telling you in the probably in the first class or in the first question of this class into the higher photon energy with femtosecond resolution. So for that let me first save. It is already saved. Okay, save, and then mm, my slides are visible. Perfect, right? So like this. See, this is NLO. uh, This is NLO. This is NLO. Non-linear opt non-linear optical material. So from this some frequency generation you can see that, see, 800 nanometer light is going inside this non-linear optical material and 600. So you are getting 600, 300, 800, 400, and then you are getting also one wavelength, which is the same formula I have written: 100, 1y 800, 1y 600, 1y 600 will get another 1y lambda. That lambda turns out to be 342 nanometer. So this wavelength you will get by this, what you call this, some frequency generation, or second order non-linear some frequency generation, something like this, the full terminology of this. So yeah, this is what I wanted to tell probably. There is nothing to tell now. Maybe let me see the question again. Fluorescence of convergence spectroscopy measures ultra-fast fluorescence decay by mixing fluorescence with delayed gate pulse in a non-linear crystal. Okay, that's so NLO is this. NLO is this here. So this whatever I have explained, this is also present here. This at this position. This is your laser. Pulse is going from here. This is dichroic. Some part of is going here. Dichroic or dichroic mirror or beam splitter. But because how, if it is dichroic, then how it will going to reflect here if the same frequency is there? So it should be like beam splitter. Oh, okay, okay, yeah, yeah, got it. So let's say it is giving 800 nanometer light, this laser. Here NLA is also present, this position. So it is here at, so till here, till NLO, from this laser to here, you are getting 800 nanometer pulse light. But after NLO, as you have seen here, after NLO, you generate. Let's say if only one light is there, so what is happen? What will be going? What will going to happen after the NLO? It will generate 400 and 800, both the lights. So after this NLO, you will get 400 and as well as 800 nanometer. So this has to be dichroic. Dichroic means it will pass after certain wavelength, and let's say dichroic mirror will going to pass from 500 to 800, and from 200 to 400 it will not going to, like, before 500 and after 800 it will not going to pass dichroic mirror. So this is a special kind of mirror. So after reaching to the dichroic, it is passing the 800 nanometer. So this is 800 nanometer, but it is not going to it will not letting pass the your 400 nanometer light. So what it will do, it will reflect this, your dichroic mirror will reflect the light. So this one is 400, this one is the 400 nanometer light, and your sample is here, your sample is here. So after going to this dichroic, light is coming here, 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 and then going to the sample. The sample, and that sample is going to be excited by your 400 nanometer laser or light, I would say, because laser is 800. So you will get the fluorescence light from this. So after the excitation, after this 400 nanometer excitation, you will be getting the fluorescence from your sample at this position, and that light is going here in the NLO, okay, which is going to be mixed up by your original 800. So this original 800 is going here, this is your mirror, or I would it is attached with your delay stage. This is your delay stage, then here, then here, then here, then reaching to here, and then finally it is going to the NLO. So it will going to generate here 800, 400, and this this light will be your emission. After exciting to the 400, it will be the emission wavelength, and then the some frequency generation, W1, W2 light intensity. So all these wavelength, as sir has already explained, like speed of light is fixed, like 3 into 10 to the power 8. So if the speed of light is fixed, and then distance by time, which means this is fixed, so distance is directly proportional to your time, right? So if you are directly not going to, like you are directly uh, not measuring the fluorescence, this fluorescence, because the resolution is not that high. If so, that is why, like, the I would say the fluorescence lifetime is low. That is why you cannot measure in the TCSVC instrument. But in this fluorescence upconversion, if you mix this fluorescence of this with your original 800 using this delay stage means it will move from from this position to this position. This is too dirty. How to remove this? Oh no. Where is the eraser? I have no clue. Anyway, anyway, so this delay stage, this delay stage, also I'm not able to choose another color. Anyway, so this delay stage here at this position, it will move here and there. Your delay stage. So as I've already explained, because if your fluorescence is coming from here, it will look something like this. See this, but it will be mixed with your 800. This by using the NLO, and by by moving this your delay stage, which is directly proportional this distance, because if you are moving means you are traveling some distance, so this distance is directly proportional to your time, which means your 800 light, this 800 light is fixed, but you are moving this 800 light here and there, and this is fixed. So this 800 light one time is here, another time is here, another time is here, another time is here, another time is here, after that here. So basically your this fluorescence at 400 here and 800 at delay, this position are mixing together, and you're getting the some frequency generated your emission, this lifetime measurement, generated fluorescence intensity of lifetime measurement. So this is what you are getting. See, delay time, delay time I1 omega 1 plus omega 2, this is delay time. So this is what you are getting. So this is the up conversion setup. Of course, there is one approximation is that your speed of light is fixed, 3 into 10 to the power 8 for all the wavelength. So let's say your blue light is also, I'm considering, is having the same speed. Your green light, yellow light, and red light is also having the same speed. However, they are different, but we have considered it is same. So this is the up conversion setup I have tried to explain. Probably it has helped you little bit. I have no clue because I am not getting any response. Anyway, okay, fine. Probably I have made you understand little bit. So the fluorescence upconversion, the spectroscopy measures ultra-fast fluorescence decay by mixing fluorescence with delay gate pulse in a non-linear crystal NLO. So option B is correct. Upconversion using non-linear optical mixing to convert emission into higher energy photon with femtosecond resolution. So yeah, you can ask why this setup is required. This setup is required because the resolution of the TCS-PC is not that high. If lifetime is faster, maybe like 20 picosecond or less than that, then you cannot measure by using the TCS-PC instrument. So that is why you have to use up conversion. So that is the main thing. Then there is no problem. Understood? Patlekha, Shivam, Devendra. Okay, Patlekha is fine. Shivam is fine. Okay, Devendra, you have also understood. Moving on to the next question. When a fluorophore enters a micelle, you probably know what is micelle. So when a fluorophore enters a micelle, fluorescence intensity usually increases. Because there are a lot of like increased fluorescence concentration, increase or provide a hydrophobic microenvironment, increase excitation wavelength, enhances detector sensitivity. So, okay, Shivam is writing B. Answer is written, but you must have understood. Then it will be. I'm assuming you must have understood. That is why you are answering. So, micelle reduces solvent quenching because if fluorophore is there, let's say this is your fluorophore, and it is in the solvent. I'm considering that solvent is water. So, this is water. If that situation is there, the water and this your fluorophore is constantly colliding. So this collision will decrease the this fluorescence. So, but by entering into the micelles, you know the micelles. Probably you have seen this is hydrophobic part, hydrophobic, something like this. So your fluorophore now come at this place. Okay. If that is the condition, like if that is happening, then your your interaction, your fluorophore interaction with the water molecule will going to decrease anyway. So it will, so by introducing your fluorophore into the micelle, the solvent quenching will be less. Hence, the fluorescence intensity will increase. Also, one more reason is the restrict molecular motion. If your fluorophore is having a rotation, like I know some fluorophore molecule, they are molecular rotor. They are like non-fluorescent. So how we measure the like we increase how we measure the intensity or what you call like they are molecular rotor or not. You need to keep on increasing the viscosity of your of your solvent and observe that intensity is increasing and observe that the intensity is increasing. Then you can simply find it out that there is one molecule I know, I can tell you the name, which is like this, what you call, the CPM. One CPM dye is there, coumarin dye. So that is molecular rotor. So what you mean by molecular rotor? Let's say this is one moiety, NOC, some COH, some there Y chain or something, and then one bond is there, and it is also with NO some moiety or some benzene ring, this moiety. So this bond, this this bond, this bond is flexible. So it can go this side, this one side of the molecule can uh, rotate this like in left-handed or right-handed, like any direction it can rotate. This and this one also, like they are rotating just like. So that is why we call this call these molecule a molecular rotor. So if we introduce like this molecule in a viscous solution or in a micelle, what will happen? Week 6, question 5. Which question? Oh, week 6. I am solving assignment 5. Sorry, sir. Okay, anyway. So, so molecular rotor will going to decrease. The rotation will decrease in the micelle here. So because of this restriction, like so if the rotation is there, then the non-radiative transitions are more. The non-radiative decay is there. Okay. So by introducing your molecule in this viscous solution or micelles, the rotation will decrease. Hence, your non-radiative transitions or channel will going to decrease, which will eventually increase the your fluorescence intensity. And also I believe it should increase the lifetime of the molecule. Probably. Lifetime. Because non-radiative channels are decreasing, so yes, lifetime will also going to decrease, like increase. In this case, in the micelles, lifetime will be higher. Fluorescence intensity also get higher. So answer is what hydrophobic environment B. Understood? Understood both of three of you? Shivam, Patlika, what Devendra? Devendra is saying question. Devendra is also fine. Week 6, question 5. Sorry, sir. I don't know what you are trying to say, but let us move forward. Let me check my video also. Yeah, it is saving 1 hour 37 minutes. Fine. We are on time. Okay, moving on to the next question. We have finished this year, this this year this year's assignment 5. Now this question is from last year of assignment 5. Okay, so the first question is the wavelength of the some frequency light generated by 600 nanometer, 300 nanometer light is. So the same formula, 1 by your lambda, 1 by 600, 1 by 300, then do this, 1 by lambda equal to 1 plus 2 and 2 into 2, 600 equal to 3, turns out to be 200. So lambda turns out to be 200 nanometer. A option. Shivam is fine. Patlekha Devendra. I hope there is no problem because same question. Okay, fine. Moving on to the next question. In a fluorescence upconvergence experiment, which component is primarily responsible for selecting the specific time window of the fluorescence signal for detection? This you know, this I have already told you. We need to select the time window in the fluorescence upconversion. So which primary component? Option B, yes, optical delay time line. That that is what I was saying. No, the delay. This, this delay stage. It can move here and there. So that optical delay line will select the specific time window, because I have already told you the speed equal to distance by time. speed is fixed, so distance is directly proportional to time. So if you want to measure the time or select the specific time window, because why you need to select the specific time window, because not every fluorophore is having the exact like the same time window, so you need to adjust like some one molecule is having 5 picosecond lifetime, one is having 1 picosecond a lifetime, so you need to adjust the time window. So that is why. And in explanation, what is written in a fluorescence of conversion experiment, the optical delay line is primarily responsible for selecting a specific time window of fluorescence signal for detection. This is achieved by varying the relative delay between excitation pulse and gating pulse used in the non-linear sum frequency generation process. By adjusting the delay, different time point of the fluorescence, by adjusting the delay, different time point of the fluorescence decay can be selectively measured, allowing for time result detection of ultra-fast fluorescence dynamics. Okay, all of you, should we move forward? Okay, fine. What is the primary requirement for some frequency generation to occur in a material? This probably you have heard in lecture number 21. Basically, they are asking the property of the material, which can act as a some can be used in this for this some frequency generation in the upconversion setup. So in one of the class, sir told about this centrosymmetric something. So the material should be non-centrosymmetric. Okay. So option. Okay, option B is written. The material must have centrosymmetric center. No, no, no. If it will going to have centrosymmetric center, then it will not act as a non-linear optical material. So it should lack the inversion of the symmetry or centrosymmetric nature. So option C is correct. And the explanation is written. Some frequency generation is a second order non-linear optical process in which the two input photons interact. Two input photon. These two input photons interact to produce a third photon, this third photon, with a frequency equal to the sum of the input frequency. So 800, 600, and this turns out to be 342 nanometer. So higher wavelength, lower wavelength, higher energy, or lower wavelength you will produce by these given photons. Okay, so for second order non-linear optical processes like some frequency generation to occur, the material must lack inversion symmetry. Material must lack inversion symmetry. This is because the second order non-linear susceptibility vanishes in centrosymmetric material due to symmetry constant. So only centrosymmetric material. So only non-centrosymmetric material possesses a non-zero susceptibility, which allows for efficient some frequency generation. Okay, do I have to explain it more or should move forward? Both of you are fine. What about Devendra Mani, Devendra Kumar? Okay, moving on to the next question. In a quenching experiment, both the plot I0 by I versus Q in the quenching experiment, okay, and Q0 by Q in this. Give a slope, okay, in quenching experiment, both the plot give a slope of 40, 40 molar minus 1, 40 molar minus 1. So this should be your KSB. KSB. If the total, if the value of the quenching constant is, okay, KQ is 2 into 10 to the power 8 molar minus 1 second minus 1, yes. The fluorescence lifetime of the fluorophore in the absence of the quencher is. So this is simple. KSB, you know, this KSB according to, see this formula, I0 by I is equal to 1 plus KSB Q. So slope is KSB, and the slope is equal to KQ into tau 0. KQ is this, and this KS is 40. Just calculate it out. You will get the tau 0. So it will turns out to be tau 0 equal to 40 divided by 2 into 10 to the power 8. Mole inverse will cancel out, and second, so it will be second 20 10 to the power minus 8 2 nanosecond or 20 nanosecond. 20 is also not correct, because this, then it will turns out to be, we convert into the nanosecond, 10 minus, then we have to multiply 1, so it will turns out to 200 nanosecond. Okay, oh, okay, fine. This is 10 to the power 10. I have done some mistake. 10 to the power 10. 10 to the power 10. So it will go here, 10 to the power 10, 1, yeah, 2 nanosecond. So after the calculation, it turns out to be 2 nanosecond. Calculation you can do. I'm just giving you the hint, also solving, but anyway, no problem. So option C is correct. Okay, all of you. Shivam, Patlika, okay, Devendra is also fine. Okay, moving on to the next question. The statement among the following, the statement that best differentiate the static quenching from the dynamic quenching. This you guys have to answer me, because I have solved lot of question in this class only about this static and dynamic quenching. Okay, Devendra has written some calculation about what you have written, bhai? Again, hello sir, yes, tell me. Week 6, question 5, calculation by given R0 equal to this to this to this. I think I don't have question right now, so join my next class because right now I don't have question. Yeah, I don't have question right now in my PPT. So in the next class I'll solve. Join the next class, no? You have already submitted this assignment or not? Okay, Patlika has written option A. What about oh, what about this question? Devendra, this your query I will solve in the next class because I don't have question right now. Okay, seems like nobody is interested. So I can tell you among the following statement, the first statement, static quenching involves ground state complex formation. That I have already explained. Whereas dynamic quenching occurs due to the collision interaction and leading to the non-radiative energy loss. So option A is correct. Patlika Shivam Devendra. Okay. Shivam fine. Patlika no. Devendra okay. All of you are fine. 153. 153. Okay. So moving on to the next question. Consider a case where the fluorophore F is taken in a 30 millimolar solution of SDS phase and is quenched by a gradual addition of the quencher. The total plot I0 by I versus Q is a linear slope is equal to 1 plus KSV KQ. No. I'm correct. No. This. Sorry. Wrong. Okay. Consider a case where a fluorophore F is taken in a 30 millimolar solution of SDS. So this is the concentration of SDS and is quenched by a gradual addition of the quencher. The plot I0 by I versus Q is a linear slope of 5. So slope is 5 molarity inverse. If the critical CMC of SDS is, CMC is also given, which is 8 millimolar. The concentration of the fluorophore F is 4 micromolar. Okay, concentration of the fluorophore, which is not quite probably 4 micromolar. Then the aggregation number of the micelle in 30 millimolar SDS solution is. So that slope, if you remember the equation, is N aggregate divided by S of this divided by minus of CMC. If you don't remember, I can show you, and I will going to show you. See this equation. I hope it is visible to you. So this equation, somehow this equation, and slope is N aggregate divided by concentration of the surfactant minus CMC. So slope is given, which is 5. N aggregate you need to find it out, divided by concentration of your surfactant, which is 30 millimolar, minus CMC is 8 millimolar. So millimolar is fine, and this is slope. Slope is molar. Slope is molar. Anyway, so we can calculate it out. It should be equal to, if you 22 millimolar N aggregate is equal to 5, and multiply these two, you'll get the 1110. N aggregate, then it will be 5 molar inverse minus 22 millimolar. Probably something is wrong in this question, because this is 22 millimolar and this is molar. So molar will cancel out, but millimolar means 10 to the power minus 3 should be there, which means N aggregate number turns out to be 22 multiplied by 5 equal to 1110 into 10 to the power minus 3, 0.1. So N aggregate will turns out to be 0.11, this, or it should not be millimolar, these value. Then N aggregate value turns out to be 1110, this B option. So according to this question, I should feel that it should be 30 molar or 8 molar, or this slope is 5 millimolar millimolar inverse. So I think this should be the case. Slope should be in millimolar, because this SGS concentration is and your my CMC concentration is fine, because I know that value. CMC value of SDS is 8 millimolar. That I know. So the slope should be in millimolar inwards. Then the 1110 value will come. Fine, all of you? Any confusion? Just tell me. Do Shivam, Patlika, all good? What about Devendra? Devendra is also good. Okay, fine. Okay, so I am ending this session now. 1, 2, 3, 4 questions are left. So no problem. I will I will be solving this question and the next assignment and your problem also, Devendra, in the next class. Next class will going to happen on Sunday, same time, 4 to 6 p.m. Okay, so he is saying, sir, week 6 assignment submission date is 4/3/2026. So what can we done? What can we do? What can I do? Okay, write in the that portal, no? This NPTEL portal, something is there, no? Where you can ask your query. Right there. Okay. So I will reply there. Then it will be fine. Okay, I am ending this session for now. Join on 8th of March, same time 4 to 6 p.m. Till then,